So for our first lesson, we're going to start with some functions, review, and preview. First of all, we're going to go through some definitions, starting with domain. Recall that domain is the set of all inputs of a function. Or the way I like to think of it is all the x values that you are allowed to put into a function. The range is the set of all outputs of a function. And again, the way I like to think about it is all the y values that you can get out of a function. Next are the intervals of increase and decrease. These are the intervals within a function's domain where the y value of the function gets larger as we move from left to right. And the intervals of decrease are the intervals within the function's domain where the y values of the function get smaller as you move left to right. End behavior. The end behavior graph is defined by what's going on at the ends of each graph. In which direction are the ends of the graphs heading? Are they going to infinity, negative infinity, or are they approaching a number? In other words, as x approaches infinity or negative infinity, f of x approaches what? The next definitions are vertical asymptote and horizontal. We say that the line x equals a is a vertical asymptote of the function y equals f of x if the y values are going to plus or minus infinity as x approaches the line x equals a from left to right. So what this means is if you have a graph and you have this vertical line here, if the function starts going to infinity as it approaches that vertical line, then we have a vertical asymptote. Or it can approach negative infinity from one of the sides. So for horizontal asymptote, we say that the line y equals b is a horizontal asymptote of the function y equals f of x if y approaches some number b as x approaches plus or minus infinity. So for example, if we have a graph and the graph is approaching, let's say, the x-axis, so y equals 0, as x goes to plus or minus infinity. So that picture there, the horizontal asymptote is y equals 0. And finally, our last definition is a continuous function. A function is continuous if it has no discontinuities. That is, there's no holes or breaks in its graph over the entire curve. So if we look at the two graphs above, I have one that's continuous. There's no breaks or gaps. And I have one that's discontinuous. There's definitely a break where that dotted line or that vertical asymptote is located. So let's go through some examples. So graph each function and state the domain and range, the intervals of increase and decrease, and the end behavior. So these are all the base functions that you learned in grade 11 and in grade 10 and that you'll need to know for grade 12. So starting with the first one, we have f of x is equal to x. So if we sub in our values, for example, if I want to find f at negative 3, I sub in negative 3 wherever I see an x. So we see that f of negative 3 is equal to negative 3. And you can continue and determine each of the following y values. So with that, let's graph this function. So there's our graph f of x. So now let's answer the following questions. What is the domain? So what x values can I put into this function? So hopefully you see that we could put in any x value. So we say that x is in the real number system. So that means we can put in decimals, fractions, irrational numbers, rational numbers, whatever number we choose can fit into this function. Similarly, what can we get out of this function is what we call the range. And the range in this one, we can also get out any real number. Next is the intervals of increase. So where is this function going up to the right? Well, if you look at this function, as we read it from left to right, so as we look at it this way, we see that this function is always increasing. The y values are always getting larger. So we say that f of x is increasing for all x. Next, what are the intervals of decrease? As we look left to right, this function is never decreasing. And finally, the end behavior. So what we do is we compare both ends of the graph. So we say as x goes to infinity. Well, what does that mean? That means we're looking at the graph as it goes to infinity. So this is x going to infinity. So I'm going to use this symbol here with an arrow. What is the y values? What are they doing? And you notice the y values keep on getting bigger and bigger. So the y values also go to infinity. So as x goes to infinity, our end behavior tells us that y goes to infinity. So we're going to use a short form instead for the next part then. So we're going to say as x goes to negative infinity. So I'm going to use the arrow. This means goes to negative infinity. What does y go to? Well, if we look at the graph here, as we go this direction now, as y goes to negative, or as x goes to negative infinity, we see that the y values are getting more and more negative, so our y values are also going to negative infinity. Basically, it's telling you as you look going from right to left, the graph is going downwards. As you look from left to right, the graph is continuously going upwards. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. And this tells you that you have a range of y values from negative infinity to infinity. So that's our linear function. So let's label these as we go. So this one is our linear function. All right, next one is in grade 10, we learned about quadratic functions. So same as before, if I want to find or determine the y values for this function, I sub in f at negative 3, and that means I'm going to have negative 3 squared on the right side, and negative 3 times negative 3 is 9. So now I can complete this table of values. So I have 9, and again, you can try these on your own. And then graph this function on the graph given here. So let's go through these questions once again. So starting with domain, what can I put into the function? I can choose any x value I want. So we say that x is in the reals. Similarly, I can get real numbers for the y, but there is a restriction. And we notice that this graph only exists above the x-axis and including the x-axis. So therefore, the y values have to be greater than or equal to 0. There are no y values that are negative. Next are the intervals of increase. So we say that f of x is increasing. And if you look closely on the graph, we can say on x greater than 0. So let's highlight that. That's here. We can see it's increasing as we look left to right for x values greater than 0. So this first way that I wrote it is called interval notation. A second way to write this is to use what we call set notation. And set notation looks like this. We're starting with 0, and notice I use a rounded bracket. That means we're not including 0. And I can go all the way to infinity. So this notation here is the same as this here. One's interval notation, one is set notation. Next, we look at where this function is decreasing. So as we look left to right, we see it's decreasing all the way up to 0. Or, again, we can write it using set notation from negative infinity to 0. Please note, you can use either notation. You need to understand both because answers in the back of the book may use either notation. Finally, let's look at the end behavior, and we'll use our short notation. So as x goes to infinity, you see that the y values keep on getting larger and larger, so y is going to infinity. And then if we look at x going to negative infinity, and we see that y goes to positive infinity again. As the x values get larger and larger in the negative direction, the y values get larger and larger in the positive y direction. So again, pause the video at any time and try these yourselves, and then check the work. So our next function is our cubic function. So again, we can sub in our value. We have f of negative 3, which is equal to negative 3 cubed, which is equal to minus 27. So if we plot our points, the cubic function looks something like this. So here's our function f of x. Let's go through the same steps as the last one. Again, please pause the video and try this yourself. So first of all, the domain, we know that x can be any real number. I could put any value into this function. Similarly, I can get any y value out of this function. Intervals of increase. So we see that f of x is increasing for all of x. Intervals of decrease, f of x is not decreasing or never decreases. And finally, end behavior. We see as x goes to infinity, as we get larger and larger x values, y goes to infinity, the y values get larger. And as x goes to minus infinity, y goes to minus infinity. Let's keep going. Next function, which you may have learned in grade 11 or may not have, is the absolute value function. The absolute value of any number may be thought of as the distance from 0. So if you think of it that way, then negative 3 is 3 units from 0. Negative 2 is 2 units from 0. Negative 1 is 1 unit. 0 is 0 units. 1 is 1. 2 is 2. And 3 is 3. And you see we get what appears to be two straight lines or a v. That is the absolute value function. Domain. So the domain is x can be any real number. The range, again you see that this function only exists for y values greater than or equal to 0. So y can be any real number, but it has to be greater than or equal to 0. And that makes sense because we're talking about the distance from 0, so we can't have a negative distance. Intervals of increase. So f of x is increasing on. And where does it increase? Again, if we look at this graph, we see it's increasing when x is greater than 0. So we can write that either as x greater than 0, or using our set notation, 0 to infinity. And the intervals of decrease are f of x is decreasing when x is less than 0. End behavior, you can see as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y again goes to infinity. It keeps on going up. Next function. Here is our square root function. So table of values, and this one we're going to fix up. So this should have been 1, 4, and 9. Now when you type these into your calculator, or if you think about the square root function, you can't take the square root of a negative number, so none of these should have values. However, you can square root 0. It gives you back 0. You can square root 1. You get 1, you get 2, and then you get 3. So when we're graphing the square root function, remember the square root has a domain restriction for x, that it has to be greater than or equal to 0. We cannot use negative values for the square root function. So remember, this is the inverse of y equals x squared. So domain, we already talked about this. X can be any real number. However, x has to be greater than or equal to 0. And if you look at the range, y can be any real number, but again, y has to be greater than or equal to 0. There are no negative y values for this function. The intervals of increase, hopefully you see that f of x is increasing for all of x. And notice it's increasing for all x within its domain. And we also see that it's never decreasing. And finally, the end behavior. We say as x goes to infinity, y goes to infinity. And we really can't define it in the negative direction because this function does not exist. So again, we don't worry about the end behavior where the function does not exist. All right, next base function is our reciprocal function. Or if you want to call it a rational function. So again, we sub in our values. And let's graph this function. So what's interesting about this function is we have a break. So this is a discontinuous function at x equals 0. So hopefully you can see the break here. We also have the fact that this function is approaching this line y equals 0. And since it's approaching that, we call this our horizontal asymptote. And similarly, we have a vertical asymptote. And that is because as you approach x equals 0 from the left or from the right, we see as you approach from the right, this goes to infinity. As you approach from the left, this goes to negative infinity. So if a function shoots off into positive or negative infinity as it approaches a vertical line, that's what we call a vertical asymptote. So let's go through our domain. So we see that x can be any real number. However, x cannot equal 0 because that is where we have our vertical asymptote. The range, again, y can be any real number. And again, y cannot equal 0 because of the horizontal asymptote. And this graph in particular does not cross it. However, some graphs may. Intervals of increase. So we see this graph is never increasing. However, the function is decreasing. And we can see it's decreasing on two intervals. When x is less than 0 and when x is greater than 0. At 0, it's undefined. Again, if we want to use our other notation or set notation, we can write it as. And finally, our end behavior. We can say as x goes to infinity, y, if you look at this graph, is approaching 0 or goes to 0. And similarly, as x goes to negative infinity, y is approaching 0. And this is what makes up a horizontal asymptote, that the y values approach a number. Next up is our exponential function. So again, we're just subbing our values, and you try this yourself. So if I want f at negative 3, that's equal 2 to the negative 3, which is equal to 1 over 8. And you can complete this table. And if you have questions, let me know. Let's graph this function. So domain, I can sub in any x value I choose. but there is a restriction on the y's. Y can be any real number, but you see that y has to be greater than 0. It can never equal 0. Take any x value you want, and it'll always get closer and closer to 0 if you choose a negative x value, but it'll never equal 0. Intervals of increase, we can see that's increasing on all x, and decrease, this function is never decreasing. And finally, our end behavior. As x goes to infinity, we see that y, or f of x, goes to positive infinity. However, as x goes to negative infinity, we see that y is going to 0. It's going downwards, but it's never crossing that line, y equals 0, which means, once again, this tells us we have a horizontal asymptote at y equals 0. And that is true for all exponential functions. They will have a horizontal asymptote. So the last two are trigonometric functions. So starting with sine, if you want to check these, make sure your calculator is in degree mode. So if I want f at 0, I want the sine of 0 degrees, and that's going to give me 0. If I did the sine of 90, that's going to give me 1, then 0, then negative 1, then 0. So if you recall from last year, our sine function looks like this. And remember, it's a periodic function, so we would continue on making this wave. So if I want to draw the back half of this, and notice I've only drawn 2 periods of this function. So let's look at the domain. For this function, if we're saying there's no restriction, we can put in any angle we want to, any x value. But there is a restriction on the y values. The y values can be any real number, but they're always in between -1 and including -1 and +1. For the intervals of increase and decrease, let's just look at 0 degrees to 360 degrees. So we can see it's increasing from 0 to 90 and from 270 to 360. Interval of decrease, we can see it's decreasing from 90 to 270. And notice I just used set notation. End behavior, well, this fluctuates between -1 and 1 indefinitely. So as far as sine and cosine, we're not going to worry about end behavior. So now let's go to cosine, which is the second trigonomic function you looked at last year. And it started at 1, then went down to 0, -1, 0, then 1. And if we want to draw a second cycle, there is our cosine function. Domain. X can be any real number unless you have restrictions. The range. Y can be any real number, but again, the y can only take on values from -1 to 1, including those values. Intervals of increase. So this is increasing. Let's take a look at just one cycle. From 180 to 360. And finally decreasing from 0 to 180. Again, we're not going to worry about end behavior for our periodic functions. So as a note there, we've already named each function. We've already stated horizontal, vertical asymptotes if they exist. Are any of the functions discontinuous? Well, there's technically only one that is discontinuous. This one right here is discontinuous at x equals 0. However, it is continuous everywhere else. And another way to think of continuity is this. If you can draw this function without lifting your pen off the paper, then it's a continuous function. This one looks like it has two pieces, and I can't draw it all at once. Another function that you may think is discontinuous is this function here, the square root function. However, I could draw this without lifting my pen off the paper. So this one we say is continuous in its domain. So here are two things I want you to work on. Why are the relations in today's examples called functions? And complete the worksheet assigned for today. Please note that the first few questions in the worksheet are supposed to be review questions, and they may be a bit challenging. So please ask for help if you need it. And the remaining questions are ones that relate to what we've done today.